data needed to support lunar resource assessments, and that's given by Laszlo Keszthelyi. Laszlo, are you with us? Okay, we hear you. Well, we see you. We don't hear you.
Okay, now I can thank you.
There we go.
You can hear me?
Yep.
Okay, so thank you for this opportunity to talk to you all. There's been a varied group of us at USGS have been studying how to modify our resource assessment methodologies that we use on Earth for application to the Moon. And we hope this will provide a useful framework for discussing lunar resource evaluation. So next slide. So here's the outline. We want to start by defining some terms, then very briefly describing the methodology that we think will work for evaluating lunar resources, and discuss the kind of data we need to feed into that process to assess ice near the lunar poles. Next slide. So we tried very hard to define the absolute minimum set of terms that allows a meaningful discussion of lunar resources. We want to emphasize that there are many more terms that can be included and far more definitions. On Earth, there are strict, very long, and legal definitions of many of these terms. We don't feel that lunar exploration currently is at the point that we need those legal definitions. And here we tried to hew closer to the informal terminology used by planetary scientists. So lunar resources are anything on the Moon that we can turn into a commodity. A commodity is something we can use in space, things like power, propellant, landing pads, etc. Someday people might pay for these commodities, but we didn't think we need to make that part of the definition at this point. Resources are found in deposits. If the deposits are widely distributed, like solar power or bulk regolith, we call it a continuous deposit. And finally, a reserve is a resource that can be converted into a commodity within the mission's budget, cost, power, schedule, risk, etc. So a resource cannot be called a reserve if it exceeds any of those budgets. So this is a point that I hope people will take away from this talk, is that what constitutes a reserve depends on the specifics of the mission you're trying to send. So what is a reserve is different for different missions. So next slide. So a bit more terminology, this time looking at classification for resources and reserves. Again, this is a major simplification of the schemes we tend to use on Earth, but we're looking for the minimum set that allows a meaningful discussion for the Moon. We also mix terms from energy and mineral resources classifications and try to choose terms that will be most intuitive to planetary scientists. Across the top, we have 3 classifications related to our ability to convert the resource into a commodity. And the separations are 2 key questions. First, do we have the technology to do the conversion? And second, do we have the budget to do the conversion? On the vertical axis, we have 3 bins on the level of certainty that we have in the properties of the resource. Here, speculative means we have strong theoretical reason to expect the resource to be on the Moon. We may have multiple indirect measurements supporting the presence of the deposits. We might even have a few direct measurements showing that these resources do exist, but we don't have a lot of information about them. Inferred means we have a good understanding of the properties of the resource, its quality, quantity, and variability, but we don't have it in the location of interest. We have to extrapolate from existing data. Measured means we have data from the site of interest of sufficient quality and quantity that we can robustly tell you the quantity and quality of the resource deposits in the area. You're basically interpolating from data around the site. Okay, next slide. So this leads us to quantitative resource assessments. I want to emphasize that when we use the word quantitative, we don't mean we have a number for the amount of the resource. It means we have data to assess the uncertainties and thus estimate risks. So a very important question is, how many measurements do you need to do the statistics related to this? The answer is, it depends. If you have a priori knowledge that the distribution is uniform, you only need 2 or 3 measurements to have great certainty in that value. If you know the distribution is a normal or Poisson distribution, then 10 to 12 measurements will give you a good quantification of the mean and standard deviation. But if you don't know the distribution, you don't know how much data you need. Now, it isn't totally hopeless. In practice, in general, for many geologic parameters, somewhere around 30 to 50 measurements gives you a decent sense of what the distribution looks like. However, this assumes you have a single population. For lunar ice, suppose there is recent ice deposited, say, in the last 100 million years, and ancient ice deposited, say, 4 billion years ago. These could have very distinct properties, and your statistics will be garbage if you treat them as a single population. So next slide. This is a chart that describes the methodology we came up for doing quantitative lunar resource assessments. And I won't go into any detail today, but the key point is that we break the problem into a series of smaller problems, each one depending on generating a mathematical expression for the probability distribution of some key parameters. And then these are combined in a statistically rigorous manner to produce a report. So, but today we're focusing on what kind of data you need. So next slide. And I put up a list, but other speakers already have put up a more detailed list, and we've heard over many years from many people in the community about what we need to measure. Things like the spatial distribution of the ice, its form, the contaminants, etc. What I wanted to highlight today was that if one wants to discuss reserves, you also need to consider parameters related to the excavation and processing of the ice. So in the resource classification chart, you want to move horizontally as well as vertically. And so, next slide. And so when we think about what kind of data we need for a resource evaluation campaign, what that campaign might look like, first you need to pick some sites you consider promising for ISRU. And as we've seen, we've got good orbital data that's giving us a relatively short list that has high potential. The combination of ground truth from Viper and perhaps some other missions will give you confidence in interpreting that remote sensing data. And then you want to do detailed measurements in the most promising areas to find one that meets your requirements to do the ISRU processing. And as an example, Viper has a very good set of instruments for characterizing ice. So a similar instrument suite should suffice. But to demonstrate that you can recover the resource, that you can excavate it and transport it around, landing something like Razor could do that. So the exploration of a site with a combination of a Viper-like science rover and a Razor-like excavator should be extremely powerful. In particular, it will allow you to do real 3D characterization of ice deposits with a combination of drilling and trenching. And that's my presentation for today. Thank you.
Thanks very much, Laszlo.